So previously in the last discussion we have formulated the pipe flow convection uh, problem, and we have to solve that now. So what did we do? We we introduced something t equal to, that was the main independent variable. We introduced t equal to Tb, that is the bulk mean temperature, plus a function phi and a function psi. So the function phi was only a function of eta, right? So phi was only a function of eta. Tb was only a function of z because we have integrated over the radial coordinate, and psi was the function of both z comma eta, right? Okay. So if that is now clear, then we can solve one by one. So remember that we have already solved for Tb, right? So how can we get the equation of Tb? See that I don't remember the equation of Tb, but I can always formulate that. How? So if I neglect axial conduction, and this is this is a control volume Cv, okay, and this was the pipe here, okay, this and this was the pipe. So some heat flux was going in, and right, that is q naught. So q naught, q naught into 2 pi r dx. I am not describing it again, I have already done it. That is m dot, that is rho, and velocity w, rho v into area, that is pi r square, that is the mass flow rate, into Cp into dTb, that is the bulk mean temperature. And this was not x, this was the z coordinate. So this was the z coordinate, right? So we can clearly find this dTb dz is equal to what? Q naught 2 pi r by rho, sorry, by rho and w, that is the z velocity component, pi r square Cp, and that becomes q naught. So 2 q naught and rho w r Cp. Okay, this was the equation of Tb, and the boundary condition is Tb at z equal to 0, that is equal to Tb in, right? And if it is the uniform temperature condition, then this is equal to T in. Okay. Now let us solve for phi, right? Let us solve for phi. So what was the equation of phi? I don't remember that also, so let me go back. See, I like to remember the least things, okay, but also then he will say that we have to crack gate, then how can we do that? So I have a separate channel in which I have told you that how to train your brain to remember the things, and I mean by putting least amount of effort. You don't have to mug up the formulas, okay, just like taking a copy in front of you and you are mugging up that poem or history, okay, so you don't have to mug up formulas like that. So let us come back to the convection now. So now this was the equation, right? This was the equation. So what was it? 1 minus eta square into 2r q naught by k. So let me write it. So 1 minus eta square into 2 into q naught into r by k, right? That was equal to 1 by eta. Okay, now this I can remember. 1 by eta d d eta eta d phi d eta, okay, only this, right? I think nothing more was there, okay, is fine. And what was this phi? This phi we can know from here, t minus tb minus psi. this was phi, right? Okay. Okay, so now if this phi is only a function of eta, okay, we know that, and the boundary conditions was the boundary conditions were what? At eta equal to 0, we have d phi d eta equal to 0, that's the symmetry condition, and at eta equal to 1, that is the wall, we have d phi d eta is equal to what? So we have the constant heat flux, right? So we can always derive this. How we can derive this? That is dt dr. Okay, this we know. This is equal to minus q naught by k at wall. So d phi d eta into 1 by r is equal to minus q naught by k. So this becomes minus q naught into r by k. So am I right? Let me see it. Okay. So the heat flux was into the fluid, right? Heat flux was into the fluid, so it will be the plus. Why plus? Because minus k del T del R, right? This is the heat flux in the increasing radius direction. I have explained it. Okay, and that is minus q, because q is entering into the pipe, not it is leaving. So then both sides, so this will be plus. Okay. Okay. So now let us see that can we have a function satisfying this? Okay, can we have a function satisfying this thing? So let us see that, right? Okay. So here now we have to solve this. It is not so difficult actually. So this equation, what will be? So dd eta of eta into d phi d eta, that is equal to 1 minus eta square into eta 2 q naught r by k, right? We have to just be careful about the steps. So this is equal to, we have to integrate, so eta minus eta cube d eta, right, and this whole into 2 q naught r by k plus c1. Okay, then we have this is equal to eta square by 2 minus eta to the power 4 by 4, right, 2 q naught r by k plus c1 by eta, right? So we already have this, and here we also have a by eta, because this eta I have to take it into the right hand side. So d phi d eta is equal to eta by 2 minus eta cube by 4, okay, into 2 q naught by r plus c1 by this. Okay, so now you put the boundary condition that at eta equal to 0. Okay, so let me write it, I don't have to write it again. So at eta equal to 0 we have this, right, this one. So at eta equal to 0, this term goes to 0 because eta equal to 0, and this is also 0, but this goes to infinity, so that is why C1 must be 0, C1 cannot exist, right, C1 must be 0. So we get, right, d phi d eta, that is equal to eta by 2 minus eta cube by 4 into 2 q naught r by k. That means your phi will be, okay, so your phi will be eta square by 4, right, minus eta to the power 4 by 16 into 2 q naught r by k. So that will be equal to eta square by 2 minus eta to the power 4 by 8 into q naught r by k. Okay, and here it is the constant of integration, right, so plus c2. Okay, so now we have another condition that you see that phi is not a function of z, right. Okay, so d phi dz is equal to 0, right. So and what is phi b? So phi b we have to integrate it with respect to r. Okay, so phi was not a function of z, so definitely phi b is not a function of z, and we have also shown that phi b is equal to 0. Okay, because phi equal to t minus tb. Okay, so this we have shown, right. So okay, so here now phi b is equal to 0. Apply this here to find the constant c2. So now from this equation, what will be phi b? Phi b will be phi w 2 pi r dr, right. Sorry, this is not capital R. 2 pi r dr 0 to r by w 2 pi r dr. Okay, 0 to r. Now this is phi into w by w average. Okay, so now let me not jump the step. Okay, so this will be phi w 2 pi r dr. Now this I have shown that this is the w average into the cross section area pi r square. Okay, so pi and pi cancels out, right, and what I can do, I can here write w by w average and then 2 into r by r, and 1 r I will take dr by r here. Okay, so now this will become 0 to 1 because the limit of r by r is 0 to 1. So this will be equal to what? This will be equal to 0 to 1 phi, and for Hagen-Poiseuille flow w by w average is 2 into 1 minus eta square. Okay, so into 2 is already there, into eta into d of this minus this. Okay, so this is equal to this, so 2 phi 1 minus eta square 2 eta d eta, and here it will be 4 not 2. Okay, so today this one note is behaving badly. Okay, okay, so this is done. and we have also the expression of phi in terms of eta, right? Okay, so this is just a polynomial integration. You can see if I put the expression of phi here, so I have written here 4, so let me not write this 2. So this will be this, and eta square by 4 minus eta to the power 4 by 8 into q naught r by k plus c2 into 1 minus eta square into 4 into eta d eta, right? You can see there are just the powers of eta coming. So they uh, so this is a very straightforward integration, but the the problem is that you have to be careful during the algebraic manipulation. Okay, so that is the only catch, you have to be careful. Okay, okay, so now after performing this, I am not doing this. Okay, this is just a mathematical task, and this does not have any trick. But one idea I can tell you, that is, you see here that you are having this function common, and what function, that is, you have something eta to the power something power m into 1 minus eta square. Okay, or maybe more. Yes, you have that in common, and yes, you have that in common. I mean, if you multiply this with this, then this m will be what, 3. If you multiply this with this, then this m will be 5. If you multiply this with this constant, then this m will be simply 1, right? So if you can do that, then you can you can first find this one, 0 to 1. Okay, then you will get an expression in terms of m. Okay, and then you can put the value of m for different uh, for the different powers of eta. Otherwise you can do it by yourself in a straightforward manner, that is also okay. So after doing that, what you will get is this C2. Okay, C2 is equal to uh, what, C2, C2 will be equal to this minus 7 by 4 q naught r by k. Obviously I don't remember this also, I have this written, I mean I have done it before, so I have this written. Okay, so ultimately this phi becomes, okay, q naught r by k into eta square minus eta to the power 4 by 4, okay, by 7 by 24. Okay, so if I have done it right, let me see what was the eta. So eta was this, right? So maybe I have done a silly mistake. Let me see. There is a 2 here, that is fine. The equation is correct here. Okay, the equation is correct, and we have eta into d phi d eta, is we have to integrate this. We have done it right. So then eta square by 2 into 2. Okay, that is fine. Then we have to again integrate this, so eta cube. Okay, so eta, again eta square by 4 and eta to the power 4 by 16, right? So if that is correct, then this is 8 and this is coming as 2. So is it right or wrong? Because I have done it earlier, but the expression of phi, this was not like this. Okay, and that is why I am being concerned. Okay, so let me see it from the one's scratch. Okay, so this is 2 here and this is 2r. Okay, now I think I got the mistake. Here we had a 2 and here also we had a 2. So this will be here 4. All this will be 4. This will be 4. Now it is fine. Okay. So the expression that we should get is, so just modify this. Okay. This is a silly mistake and I apologize for that. This is 4. Okay. So this is 4. You don't need to modify it so much. Hey, this will be 4, this is 4, this is 4, this is also 4, right? This is again 4, 4, and if these are 4, then this will be here, this will be 1, this will be 4. Okay, okay. Now it is correct. I really apologize for that. So now we got the function of eta. Okay. So now let us try to find the Nusselt number and the heat flux. So remember that this is not a function of z. Okay, that is at any z this is valid. Okay, and also there is no boundary condition like z equal to 0, phi equal to this. Okay, so there is no boundary condition for phi like that. Okay. So this will be valid actually for large z's in the practical situation. So now what can we do? So this is the phi, and phi is equal to t minus tb. Okay. So now we have to find the Nusselt number. So Nusselt number is what? H into d by k, right? So H is equal to q wall. Okay. So whenever I am writing q wall, my convention is that heat is going into the fluid. Now, when can heat penetrate into the fluid? That means it has to be T wall minus TB into H, right? That should be the Q wall. Then only I know that T wall, if T wall is greater than TB, then my Q wall is positive. That means the heat is penetrating into the fluid. But if T wall is less than TB, then this expression is giving me negative QW, and that will mean that the heat flux is going out from the fluid, right? So this will be Q wall by TW by TB into 2R by K. Another style of writing is QR at R equal to R. Now this the moment I write QR, that means that this is the heat flux that is going towards the increasing R. That means it is leaving the fluid, because this is the increasing R. Okay, this is the increasing R, that means it is leaving the fluid. So now I have to write TB minus T wall into 2R by K. But QR at R equal to capital R is equal to minus QW. So that means these two expressions are essentially the same. Okay, these two expressions are essentially the same. Okay, so now this Q wall I have to find. Q wall is Q at R equal to R, that is minus Q, uh, actually del T del R. Okay, at r equal to r. Okay, so this will be minus k d phi, okay, d phi dr d phi d eta into 1 by r at eta equal to 1. So this will be minus k by r into d phi d eta. So d phi d eta is what? D phi d eta is uh, q naught r by k into 2 eta minus eta cube, right? Okay, so I have to put eta equal to 1, so this is eta equal to 1, and this becomes minus k by r q naught r by k into 2 minus 1. Okay, okay, and that is minus q naught. So we already know that, that is q all equal to minus q naught. Okay, so it is so it was well known, and I have also proved that. Okay, this is minus. Yes, now it is okay, because q naught is entering the fluid. Okay, so q, so this is also equal to q wall, because q wall is also entering to the fluid, and this is equal to minus of this, because this is leaving the fluid. So now my Nusselt number will be q naught by Tb minus T wall, that is what, phi b. Sorry, that is not phi b, phi is equal to T minus Tb. So phi at r equal to r, or phi at eta equal to 1, because phi is a function of eta. So phi of 1 equal to T wall minus Tb. Okay, so phi of 1 is what? That is here q naught r by k into 1 minus 1 by 4 minus 7 by 24, correct? And that is equal to q naught r by k 24 minus 6 minus 7, and that is equal to 11 by 24, right? q naught into r by k. So this is equal to T wall minus Tb. So this is phi of 1 into what, 2r by k, and this is equal to q naught. So phi of 1 is 11 by 24, q naught r by k into 2r by k. So r by k cancels out, q naught cancels out, and this becomes 48 by 11, that is 4.36 maybe. Okay, so that means Nusselt number at large z. Okay, so this is valid for large z only. Why? Okay, so because you see that the solution is not complete yet. Okay, the solution is not complete yet, we have to find the psi also. Okay, so we have to here find the psi also, and for that what we can do is we have the governing equation of psi, right? So we have the governing equation of psi here, and that was similar to the governing equation of the actual independent variable, that is the temperature, right? So here it is the governing equation of psi, where I have written it. So the governing equation of psi is problem 3. Okay, so maybe I have written it here. Okay, so this was the governing equation of psi, and this is exactly same in the same form with that of temperature. The boundary conditions are also exactly of the same form, but we have derived the boundary conditions very judiciously. Okay, so now we have to solve this psi we have to solve for this psi by a method called the separation of variable. Okay, separation of variable. Okay, and after that you will get a solution where if you put the limit z tends to infinity of psi, that will go to 0. Okay, and that directly means t equal to, okay, tb plus phi plus psi. Okay, so tb plus phi plus psi. So if we take this z tends to infinity, then this psi goes to 0, then this t equal to tb plus phi. Okay, so you see my actual definition of phi was phi equals to t minus tb minus psi. So then you can argue that yes, t is a function of, I mean, uh, both r and z. Okay, then tb is a function of z only, and psi is a function of both uh, eta and z, or r and z. Then how can phi be a function of only eta? Well, that can be happen, I mean, that can happen. How that can happen? So you see that if a is a function of x only, and if a equal to b plus c, b is a function of x and y, so maybe b is equal to x plus y, and c is a function of again x plus y. Okay, so maybe c is equal to x square minus y. So then they can be cancelled out to get a as a function of x. So here there is uh, there is nothing wrong in telling that phi is a function of eta. Mathematically it is correct, but now you can argue that yes, you have taken during during uh, during the use of this condition phi b equal to 0, we have taken phi equal to t minus tb. Yes, that was a catch. You can argue with me in that point, but you can see that as we derive the solution for psi, as psi is tending to 0, as psi is tending to 0, sorry, at z is tending to infinity, that is for the large sets, psi is tending to 0. So if psi is tending to 0, now it is valid, that is phi equal to t minus tb. Okay, so this solution is, that is why valid for only large z, and large z means it is the thermally fully developed, thermally as well as hydrodynamically. Okay, so this is just the solution for nu equal to constant. Nu is not a function of z, nu is not a function of r, and this is only valid for a large z and for a thermally as well as hydrodynamically fully developed flow. Okay, now this solution for psi, this will uh, this will involve the method of separation of variable. Okay, so after this we will be doing the thermally developing flow. Okay, and there also we have to solve the problem by the separation of variable method. Okay, so I will solve that in the next discussion by the method of separation of variable, and your homework will be to solve for this psi. So I can't emphasize on it enough, I can't tell it enough, that is, don't see a problem like that is, I mean, like an individual problem, that is, I know only this problem, that is the forced convection in a pipe. You have to have the mentality to identify that yes, the governing equation for the psi in case of the forced convection, and the governing equation for the thermally developing flow problem, those are the same, and the boundary conditions are also the same. Now mathematics does not know that if it is the problem of the thermally developing flow, or it is the problem of a forced convection flow. So mathematics will remain same. So you cannot say, I mean, it is actually uh, logicless to say that I knew the solution of hot psi, but I don't know the solution of the thermally developing flow, or the vice versa. Okay, so your homework will be, after I solve the thermal developing flow by the separation of variable method, to solve for this psi and check if you are getting that limit z tends to infinity, psi is equal to 0. Okay, So I am leaving this up to you. Okay. So this we have solved for nu equal to 4.36. Okay. So our next discussion will be of the thermally developing flow for an isothermal flat plate. Okay. So just let me pose the problem here, and we will formulate uh, and solve the problem in the next discussion. So the next problem is thermally developing flow for an isothermal pipe. Isothermal pipe means the wall of the pipe is isothermal. Okay, and here the flow is also hydrodynamically developed. Okay, hydrodynamically developed. Okay, so what we have is we have a pipe like this. Okay, and this will be the center line. Okay, so for the if this is the thermal boundary layer. Okay, okay, so this is the thermal boundary layer, and here it is here it has become the boundary layers has been joined, and the fully developed flow, thermally fully developed flow is being started after this, that is thermally fully developed flow. Okay, now the hydrodynamically fully developed flow that is already in this region. Okay, or maybe what you can say is, this is not the correct description of the problem. Okay, that is the pipe was very long, so the inlet of the pipe that is not here, let me cut it and move it here. Okay, okay, so the pipe is actually very long. Okay, now the inlet is here, the flow is here. Okay, so the flow has become hydrodynamically fully developed here, and so after this, maybe after this point, because we will have a field region, so this will be the hydrodynamically fully developed flow, right? So and after this, from any particular region, say at this region, you have started heating the plate. Okay, you have started heating the plate, and you have maintained a temperature T wall here. Okay, that is greater than T in, and T in is this, that is the temperature profile here. So T in is here. Okay, this is T in. So T wall, it can be more than T in, it can be less than T in. Okay, so we are interested to find the solution in this region. Okay, in this region, that is the thermally developing region. So the problem description is clear. I hope it is clear to you. We will solve this problem in the next discussion, and up till then, goodbye, take care, and thank you. You can always post your doubts in the comment box, or if you need any help. So up till then, goodbye.